Hi, this is Professor Fernandez, and in this video, we are going to work out an example of finding the volume of a solid, knowing the cross sections, and specifically that they are triangles. This is an example that comes from the notes from lesson 28 in this Calc 2 course. You'll find those notes at this website along with these other resources. Okay, so first let me just go over the theorem. I'll zoom in here on the lower right-hand side. That gives us information about how to find the volumes of solids with known cross sections. Okay, so first of all, the word cross section, right? So let me draw you a picture. Here is, I'm going to draw a really bad loaf of bread, right? But here is kind of a loaf of bread, not that bad. A cross section is when you slice the loaf of bread, right? You slice it that way to obtain a loaf, a slice of bread, right? So that would be the slice of bread that we obtain over here, right? And we would call that a cross section. We can put axes on here, and if we had an x-axis going this way, then the slice of bread we would obtain would be perpendicular, right? Perpendicular to the x-axis. Okay, so that cross section, perpendicular to the x-axis, has an area. And that area may depend on x, so we'll call that a sub x. You can imagine if the solid gets much more complicated, not a rectanguloid, kind of like I drew, but something like this, right? Then those cross sections, right, they're going to vary in the area. So the area is going to be a function of where you are in x. But just like with the loaf, if I wanted to find the volume of this loaf, I could just take one of those cross sections, find its area, and then multiply it by the length. Similarly, if I have a solid that is not exactly a loaf, right? But I can still slice it, then I can find the area of each one of these slices, and I can integrate it now to get the volume of the solid. That's exactly what this formula down here says. So this theorem says if A of x is the cross-sectional area perpendicular to the x-axis, then the volume of the solid is integral of this cross-sectional area dx. So the second part of this theorem, by the way, says the same thing, but just if you take this picture and you just flip it around, right? Maybe cross sections are taken perpendicular to the y-axis. Okay, so I'm going to illustrate the first part of that theorem here with this example. So let's take a look at the example. It says find the volume of the solid whose base is the region bounded by the graphs of this. So all of this gives us the base of the region. We'll picture that in a minute. And whose cross sections, there's the phrase perpendicular to the x-axis, are equilateral triangles. So that's a lot, right? That's a lot to digest, I know. So I've included here a diagram of what's going on. First of all, f of x, g of x. Let's just plot this in the plane because we can definitely do that. So this is y equals 1 minus x over 2. When x is 0, y is 1. When x is 2, y is 0. So this is the graph of the function f of x. And then over here, let's plot this one. Y equals negative 1 plus x over 2. When x is 0, y value is negative 1. When x is 2, the y value is 0 again. There we go. And then x equals 0 is the y-axis, right? So that's over here. So this region in here is the base of my solid. And the base of the solid, right? From there, I get the cross sections perpendicular to the x-axis being equilateral triangles. Meaning if I draw a little line here, if I could pop this out of the page, right, then the triangles will go that way. Right, so it's kind of what I'm drawing over here now. So actually, let me keep the picture consistent to what you're seeing on the right-hand side there. So here is y, here is x, here's f of x that we've drawn, here's g of x that we've drawn, and then if I take a little base here and then I pop it out, then I make a triangle, and it's an equilateral triangle, meaning that this side length, same as that one, same as that one. You can see as I change the base, maybe this is the base back here, I get a bigger triangle because the base, the blue line segment is bigger, right? So again, equilateral triangle. And then I kind of connect these to make this giant kind of pyramid-like solid, this blue thing pictured over here. Okay, so that's a lot of information about the geometry and sort of what's going on. So now let's go back to how we find the volume of this solid, right? Remember, the volume is going to be integral from a to b of a of x dx. So there are three things we got to find. We need the cross-sectional area, we need A, and we need B. Okay, the simplest of these to find is A and B because those are the extent, horizontal extent in terms of x of the solid. And if we look at this picture, this is why it helps to draw the two-dimensional version, the base of the solid. If we look at this picture, the leftmost extent is 0, so we're going to put a 0 here for A, and the rightmost extent is 2, so we're going to put a 2 here for B. Okay, so now we have integral from 0 to 2 of a of x dx. And what is a of x? Okay, well, that's the area of each cross section. So two places to look at for that. We can look at this triangle over here. We can also, if I delete that part that I popped up, we can look at this segment over here. All right, so these are the two places that we're going to look at. To find the area of that cross section, we're going to note, first of all, that it's an equilateral triangle. So I'm reminding you down here, let me zoom in here, of the area of an equilateral triangle. If the base length is b, or any other length, because equilateral means it's same side length, then the area is root 3 over 4 times b squared. You can derive this formula by dropping down here perpendicular and then using the Pythagorean theorem, the area of each of these triangles and adding it up. We won't do that in this video. We'll just take this formula as given. And then notice, therefore, that all we need to find the area of those equilateral triangles, cross sections in this example, is the base length. So if we zoom out here, right, we go back to this picture, all I need is the length of this base, right? How long is this? Okay. So then I'm going to go back here to the two-dimensional picture, and therefore all I need is this. This is the base of that equilateral triangle that comes up in 3 dimensions. And I kind of erased the g of x on here, but you can tell that this base length is the y value of f, right there, minus the y value of g, right? In other words, f of x minus g of x. So base b, or just write b, so b equals f of x minus g of x. So we go back up here, we know what f of x is, we'll put it in there, 1 minus x over 2. Minus, we have g of x, put it in there, x over 2 minus 1. So that gives us a 1 minus x over 2 minus x over 2 plus 1. So we get 2 minus x. So that's b. And now we just go ahead and apply the formula for the area of the equilateral triangle with that base. So that's root 3 over 4 times 2 minus x squared. Okay, and then so to clear the clutter here and kind of review where we're at and what we've gotten to so far, right? What we have determined is that if we go back and look at this solid, the area of this particular triangle, right, a of x, the area of this cross-sectional equilateral triangle is root 3 over 4, 2 minus x squared. And then earlier we had said that the volume was integral from 0 to 2 of a of x dx. So now you can see we're just going to take that function, put it in there as the integrand, and then integrate. Okay, so let's do that. So our volume is integral from 0 to 2 of root 3 over 4 times 2 minus x squared dx. So I'm going to pop out the root 3 over 4 here. And then at this point, you have a couple of options, at least 3. One of them is to square this out, right? So 4 minus 4x plus x squared. You could do that, and then you integrate term by term. Evaluate it from 0 to 2. That's option 1. Option 2 would be to use a u substitution. U is 2 minus x. Du is minus dx, and go ahead with that. Option 3 is to just do this kind of u substitution on the fly. Right, so the antiderivative of this is going to be this to the third, right, over 3. And then you can kind of check your work, right? The derivative of this, we'd use a chain rule. We'd bring down to 3, and then we'd multiply by -1, and then we still have the 3. So those will go away. And this is one of the reasons you check your work, because you see there's a minus sign there that we don't want to be there because it's not in the integrand. So what we do is we put the minus sign in front. All right, so what I've just done is, again, like I said earlier, done the u substitution effectively on the fly. You could do one of those earlier two methods that I mentioned to systematize this and kind of slow it down a bit. Okay, so if we evaluate all this, right, I'll skip through all the evaluation steps. You end up getting 2 root 3 over 3. And therefore, that is the volume of this solid that's shown here in blue using these cross sections that are equilateral triangles. Okay, thanks for watching.